everyone, to another Formal Languages and Neural Network seminar. Today we have Justin DeBenedetto presenting. He received his PhD 2 years ago as part of David Chang's NLP group and is now assistant professor at the Department of Computer Science at Villanova University in Pennsylvania. And his current research lies in semantic graphs using neural networks and automata. And today we'll hear about his and David's paper on representing unordered data using complex weighted multiset automata. I'm excited having you here today, Justin. You can take it from here.
Yeah, thank you. So as was mentioned, I'm now at Villanova University as an assistant professor, but this work was completed while I was at University of Notre Dame, along with my advisor, David Chang. So this is presented originally ICML 2020, and I'll be going over representing unordered data using complex weighted multiset automata. What is the data we're working with? Why are we moving to complex weights? What do we gain by doing so? So as an overview, we'll kind of motivate the problem. What is this data that we're working with? Why do we need something like multiset automata? Then more specifically, what are multiset automata? Why are they good for this situation? What is some of the theory we can use to improve the multiset automata so that they're more useful in neural networks? Then we'll look at where are they already in neural networks? Where can we use them in neural networks? What do we gain by doing so? So there are various ways that unordered data naturally arises. The one that drew us to this problem is modeling edges incident to a node. So if you've got a graph, you've got some edge labels. Here we can see we've got 3 different edges labeled A, one labeled B, one C. So not only is this unordered, so you'd think set, but additionally we've got different A edges, so this is a multi-set. Point cloud classification, you've got points on the surface of some object. Given those, can you classify the underlying object? There's not necessarily an inherent ordering to these points. They have a location in space, but they don't necessarily have an order beyond that. And the 3D image reconstruction, given a variety of 2-dimensional viewpoints, how can you put these together, figure out how they come together to reconstruct the 3D image behind them? And the applications here move quite beyond this. Unordered data naturally arises in a lot of different settings. But what we can see here is we want inputs that come in any order and potentially repetition in those inputs. So it's not just a set, but a multi-set. There's existing work prior to ours. In 2017, this deep sets model was published. The idea was you compute a representation for each input in parallel, apply some commutative function, which is going to discard the ordering information. I use some here because that's what they used in the experiments that we use in our paper as well. And then the rest of the network can do whatever it wants with it. So in general, make some representation, which is element by element, have some commutative function to combine them, and then whatever the network can do beyond that is really up to the use case. So for us, the representation we wanted, given that we're applying this to multisets, is to use multiset automata. This is a variant of a weighted finite state automata where the input order does not affect the output weights. So here we can see for the automaton M2, if you start in state Q1, you can transition on either a B or an A. If we take the transition on B, we go to Q2, transition on A, we're at Q4. So that's an accepted string, BA. Likewise, AB takes a different path, but is accepted as well. So whichever order, A, B, or BA, you get the same weight, you get the same strings accepted. A couple of things that are nice about this. One is that we've got unordered data. We don't have to artificially impose some ordering on it ahead of time to then process it. We can just process it as we get it in its unordered fashion. And additionally, we can implement this within a neural network, and we show how to do that. So the summary of the contributions, and we'll go into each of these in depth, but drawing your attention to where we're heading in this. Multiset automata can be approximated by complex diagonal automata. We show not only how to do that, but why we want to do that. The existing network, the transformer network, quite a popular one, uses position encodings that turn out to be a special case of our representation. So if you set the parameters just right, then we exactly match the transformer's position encodings. If you let them learn beyond there, then it can go beyond that. We then take that deep sets paper, take their network. We show that it can learn our representation, so we can move from real to complex weights. And when we do so, not only do we match their performance on one of the tasks that they showed LSTMs and GRUs struggle with, but we can actually extend the task in a way that our network does well, and the deep sets network itself can't handle it either. Okay, so diving more into multi-set automata. State diagrams are probably familiar to everyone. So we have on the left here the state diagram, initial weight 1 coming into state Q1. And we capture that on the right in its matrix representation. So lambda sub 1. We've got a 1 on state 1 saying its initial, zeros on states 2 and 3. And throughout this work, we're primarily going to be appealing to the matrix representation. And we allow as many initial states as needed, as many final states as needed. We do not have epsilon transitions, so we're going to stick with this matrix representation, but for a variety of the examples, I'll show both the state diagram and the matrix representation, so whichever one you're more familiar with, you can kind of translate between them. Okay, so we've got initial weight 1 at state 1. If we then read an input of A, we can transition state 1 to 2, 2 to 3, 3 back to 1, and all that information is captured in the transition matrix, mu1. So mu1 of A, we've got the row is saying where you're coming from, column is where you're going to. So from state 1 to state 2, you can transition on an A with weight 1, 2 to 3 with weight 1, 3 to 1 with weight 1. And again, these weights, they don't have to be binary weighted. I stick with binary weighted in examples just because it's easier to track through. But in practice, these can be any real weights. Okay, so given this, now if we're looking at where we are after reading part of an input, we refer to that as the forward weight. So the forward weight of some string. So here we're going to start with A. You apply the initial weights, multiply in the transition weights, and you get what states you're currently in. Here, given that it's binary weighted, we're not in state 1, we are in state 2, we're not in state 3. If you want to continue reading symbols, you just continue to apply these transition matrices. So lambda, that initial vector, times mu now gets you where you are. If you've read 2 A's, you're now in state 3. You read another A, you transition back to state 1. And so using this matrix representation, we're just doing vector times matrix times matrix times matrix, and do that as far as we need to, as long as the string. Okay, so now once we're here, at some point, we want to stop and find what is the actual weight. When we want the actual weight, that's where we're then going to apply our final weights captured in row. So if you apply the final weights to any of these forward weights, you get the actual weight of the string. So this automaton assigns string A weight 0, so it rejects it. Assigns AA weight 0, so it's rejected. Assigns AAA weight 1, it's accepted. And that matches both the state diagram if you track through it, as well as this matrix representation. So these representations are interchangeable. You can use one or the other. We're going to primarily build around the matrix representation, but these are interchangeable. So at any point, you could convert from one to the other. Nothing is lost. All right, what if we kind of scale it up? So now instead of 3 states, we have 4. So now each of our vectors has dimension 4. Each of our transition matrices is 4 by 4. So as the states scale up, so do the sizes of the vectors and the matrices. Additionally, we don't need to rely on just one transition, one symbol. We could have more than one. So if our alphabet contains here A and B, we need a transition matrix for each one. So now M2, it's a weighted finite automaton. It accepts A, B, and BA. This is the example we saw earlier. And we could see its matrix representation on the right. Once again, if you want to process a string, apply lambda, do matrix multiplication or vector matrix multiplication with whichever corresponding mu, and keep going until eventually you're going to apply a row to get the weights out. So this all works just like the prior example, but we can see you can have as many input symbols as you need. You just need one transition matrix for each one. And the size of the transition matrices, the size of these vectors scale with the number of states. In particular, both examples that we've seen, M1 and M2, are multiset finite automata. So formally, a k-weighted multiset finite automaton is one whose transition matrices commute pairwise. So here we've got two input symbols, A and B. And if you take mu2A, mu2B, and you flip them the other way, mu2B, mu2A, you get the same results. So it doesn't matter which order you apply these transition matrices, you're going to get the same result out. And if you have more than two inputs, say you have 10, you're doing this pairwise. So every pair has to be commutative, and then collectively you can move these matrices around so that now any order in which you read the input symbols, you're going to get the same results coming out. All right, so this is great. We have our representation. Now we want to actually learn something. We said that our objective is to use this in a neural network. To do that, we need to be able to learn these weights, these parameters. So we set it up. We say, let's start with 3 states, 2 input symbols. Now we can see at the bottom here, we have 18 parameters we want to learn. 18, it's a small number. It seems like we should be able to learn that. So maybe we set this up. We say mean squared error is what we're going to optimize for. We're going to have multi-sets and their corresponding weights as our training examples. You set it running, and there's no guarantee. And in fact, it's almost certainly not going to end up being commutative if you don't impose any additional constraints. So we want to impose those constraints. We say, all right, now let's make it so that what we have at the bottom there, that equality has to hold. So we're going to impose some constraints here, either soft constraints through some sort of regularizer, or hard constraints where we actually have to figure out which parameters are linked, how their updates have to correspond. And this gets a lot more tricky. Here we only have 18 parameters, but already we're imposing a lot of constraints on them. If we scale this up to, say, 100 states, we've got 100 by 100 for each of these transition matrices. Maybe we have 15 input symbols. Now we have a lot of constraints, and so much of the computation is going towards imposing these constraints as compared to actually trying to learn from the examples. So that's not a good setting. We don't want to be stuck there. Luckily, every square matrix, and this is why we're viewing this matrix representation, every square matrix, in particular real square matrix, is close to a complex diagonalizable matrix. Why is this a good thing? Well, diagonal matrices are really nice to work with. They're commutative just automatically. If you have 2 diagonal matrices, you're really just multiplying the diagonal the entries on the diagonal, so you can move them around freely. Commutativity just comes for free. Additionally, it's not like we have to impose some harsh constraints on it. We just don't learn anything that's not on the diagonal, set them all to 0. We're only learning the diagonal entries. So it's really easy to constrain, guarantees us commutativity. There's no sort of reliance on regularizers or trying to figure out a lot of different constraints on it. When it works, it's a really nice way to set it up. Additionally, we don't need to store all the 0 entries. So now our matrices, which were number of states by number of states, turns into, you just store the diagonal. You can treat it as a vector. So we go from O of D squared space down to O of D space for storage. Multiplication was previously matrix matrix. Now we just have diagonal entries. There's no off diagonals. It means you're actually just doing element-wise multiplication. We move from matrix matrix multiplication down to just element-wise, so O of D for multiplication. So big gain in storage space, big gain in the computation complexity. So overall, really nice when we can use these. So our approach is, since we get these gains, let's go ahead and try to use them and see where are there restrictions. So what is that trade-off? We can see we're moving from real to complex, but are there other constraints we need to put? Are there other restrictions on this? And we can see here that now this commutativity, again, comes for free. You're just multiplying. So x1 times y1 is the same as y1 times x1, assuming that you're using these complex weights here. Okay, so to be a little bit more formal, since diagonalizability may be something you have more or less familiarity with, a matrix is diagonalizable if there exist matrices P and D, such that D is diagonal, as we saw in that last slide, only entries on the main diagonal. Everything else is 0. And A equals PD P inverse. So we have an invertible matrix P, it's diagonal matrix D, and together they show us how we can convert A into its diagonal representation D. How are we going to use that? Well, we saw previously we're just kind of multiplying vector times matrix times matrix times vector. So we're going to try to apply that here. So we're going to say, start with our multiset automaton. We've got initial weights, transition weights, final weights. We're going to try to diagonalize our transition matrix. So find some P d sub A, P inverse that allows us to make that transition. And then we'll make some replacements. We'll say, instead of lambda, we're going to do lambda times P. So we're going to call that lambda prime. Our transitions are now just going to be those diagonal transition matrices with complex weights. And then we're going to change our row vector to be P inverse times rho and call that rho prime. So effectively, if we have, let's say, AAA as our input string and we want to compute its weight, we start normal way, lambda times mu times mu times mu times rho. Got a whole bunch of matrix multiplications in there. Do our substitution that we found, this PD P inverse. All the P's and P inverses that occur in the middle cancel out. You're left with just lambda times P, which in particular you compute once. You don't need to compute that for every string. You just compute that once when you form your automaton. dA times dA times dA. These are then our new transition matrices. Effectively, they're vectors. You're just doing element-wise multiplication. So here I'm grouping it together saying mu prime to the third because you're really just raising every element to the third. You're not doing any matrix-matrix multiplication here. And then finally, rho prime, again, you just compute that once. You don't need to recompute that for every string. So this simplifies it greatly. Now, instead of vector times matrix times matrix times matrix times vector, we're down to just these vector times vector element-wise multiplications. And in fact, we can even push weights from rho prime onto lambda prime if we want to simplify this further and kind of reduce the effect of rho here.
Sorry, Justin, Frank has a question.
Yes.
Yeah, sorry for interrupting, but maybe stupid question, but why doesn't have P the index A?
Yes, so that's very next thing here. The reason why is when we move beyond one matrix, we want just a single P. We don't want one that corresponds to each one. So yeah, that moves perfectly into this next definition. If we have two or more matrices, we actually want to get just a single P that diagonalizes all of them at once. So if we have, let's say, just A and B, they are simultaneously diagonalizable if there exists one matrix P and then a diagonal matrix for each of our original matrices, so D sub A, D sub B, such that the D matrices are diagonal and that single P invertible matrix applies to each one of these. So A equals PDP inverse, B equals PDP inverse for the corresponding diagonal matrix. Now, why we want to do that, in our example that we saw in the middle of the slide, we have all these P inverse P's canceling out in the middle. We want to maintain that cancellation. So we want just a single P. If we had a different P for A and for B, then we've got diagonal matrices in there, but we still have P sub A inverse multiplying P sub B. That's not going to cancel. We still have matrix-matrix multiplication. So in order to take full advantage of this, we need not only that each one is individually diagonalizable, but they're collectively diagonalizable, simultaneously diagonalizable by the same P matrix. Okay, and this moves beyond two as well. Just however many we have, we need a diagonal matrix for each and a single P that diagonalizes all of them at once. All right, so this is the goal. Let's see how it works. Our first example, we had just one input symbol. We had A. We can diagonalize that matrix. We do so. We apply the weights then, as we saw in the last slide, we get our lambda prime. Now every state is initial with weight 1/3. Got our rho prime, every state is final with weight 1. And we've got our diagonal transition matrix. Diagonal transition matrix means there are no transitions between states. You're only self-looping within states. So whenever we make this diagonal transformation, we're going to move towards every state being initial, every state being final, always self-loops. Those are three changes that are going to occur every time. It's just a matter of what are those weights. So now if you compare these two, in my opinion, kind of surprisingly, they both do have the exact same weights coming out for any given string. So if you have just the empty string, you can see in the top example, weight 1 accepts with weight 1. In the bottom example, we've got initial weights 1/3 on each. no transitions on the empty string. Then you apply row prime, you add up those 1/3, you get weight 1. If you have just the string A, state diagram on the top, you move from Q1 to Q2. Now it does not accept, so it rejects it, gives it weight 0. On this bottom diagonalized automaton, we've got a contribution of 1/3 coming from the first state, and then the second and third states are their self loops are complex conjugates, so the imaginary parts cancel, the real parts sum collectively to -1/3, and that cancels out the contribution from that first state, and so the string A gets weight 0 as desired. Likewise, AA got some contribution from the first state. We've got the imaginary parts canceling from states 2 and 3. The real parts then collectively cancel out state 1. And that works out, again, giving you weight 0. AAA, we've got weight 1/3 from the first state, weight 1/3 from the second, weight 1/3 from the third. Add them all together, you get weight 1, which is what you'd expect. That matches M1. So here we can see not only the matrix representation on the right, the benefits of now when we're taking a transition matrix, making it diagonal, but also we can see in the state diagram, what this effectively means is no transition between states. We can compute each state in parallel as much as we need to until we get to applying row. And we can push any weights we want from row onto lambda, so that really row is just summing whatever weight is, whatever the forward weights at each of these states end up being. Okay, so this worked out perfectly. This is great. Let's see what happens on our other example. So here we've got a couple more, or we've got one more state. We've got 2 input symbols instead of just 1. And if we actually try to diagonalize this, it's only approximately simultaneously diagonalizable. So here we still have, we're just finding that 1p, but our D sub A or our D sub B, they don't exactly match up with what we started with. There's a slight perturbation that's required to get them to match up. So we can look still at, we've got all these different states, they're initial, they're final, they only have self loops, that's all great. Computationally, that's going to make things a lot easier for us. Here, we're not even having to rely on complex weights. Weights of strings such as A, B, AA, BB, AA, BB. We wanted to reject all these, we still do, they all get weight 0. AB, BA, they get weight 1. Great, that's what we wanted to accept, so that's consistent. But where it's approximate is at some point we get away from 0 on things that should be 0. So strings like AAA, BBB, in any order, we're going to get epsilon to the 4th back. And again, I'll point out we don't have epsilon transition, so anytime I say epsilon, I just mean really small number. So here we can set epsilon to however small we want, to then make it so that this string gets as close to 0 as we want. It won't be 0, but we can get it as close as we want. And there's a slight trade-off here between, you need to make sure that the precision in your computer is good enough to allow the rest of these functions to have the weights that they should have. But then you balance that out with making that string, that epsilon to the smallest you want. So it's approximately simultaneously diagonalizable. It's very close, not quite 0, but effectively as close as we need it to be. Okay, so I keep saying the word close, but what does it actually mean? So there are 2 different main perspectives here. One is, what is the perturbation you have to make in order to get these transition matrices to be diagonalizable or simultaneously diagonalizable? So we can look at that, but in general, we're kind of more interested in, you're going to be applying these multiple times. So as you get longer and longer strings, do these get further and further apart from the original? So we're more interested in taking the transition matrices to some power, subtracting them from each other, looking at the norm, and what does it do? So if mu is nilpotent to start, the absolute error is bounded, we show that bound, and in the paper we show how to get there. Otherwise, we can't bound the absolute error, but we can bound the relative error. And once again, we show what that bound is and how to show it within the paper. Okay, so that worked great for unary automata. If we move on from unary to more than one input symbol, which in a lot of cases, that's where we'll be working, then we have this existing result in the literature that you have commuting matrices. They're not necessarily approximately simultaneously diagonalizable as soon as you go beyond 1. So that seems unfortunate. We need to figure out, how can we get around this? As it turns out, you can get around it with just adding more states. So if you have a weighted multiset automaton and you add more states to it, then it'll be then you can convert it to a complex weighted diagonal automaton. So while the existing result in literature, we're not contradicting that in any way. We're just saying you can get around this by possibly adding more states. Sometimes you don't have to. Other times you do have to add more states, and we show in the paper how many states we actually could have to add in the worst case. Bad news might be adding more states. Again, that bound is in the paper. The good news is the whole purpose of this, or a large purpose of this work, was to show how it functions within neural networks, how we're going to learn these weights. And so we can still decide on how many states we're going to have in our neural network and turn this into an empirical question of, are we close enough that this effectively gets where we want to be? So we'll set this up in a neural network, learn the weights, and see in practice, does this work out for us? So that moves us into now more of the empirical side of how these are going to function in neural networks, and does it match up with existing performance objectives like that. So starting off, the transformer model. This is, again, a very popular model. It came out with the sinusoidal position encodings. Those are still, I think, popular for a variety of use cases. When you have inputs to a transformer, and I tend to look at this in the natural language processing sense of, you're going to give it some words. You have a word embedding, position encoding. Transformers can be applied elsewhere where that word embedding, it's some other sort of embedding, whatever your inputs are. But the position encoding is still something that's widely used there to then give it that context of how these objects relate. So in the transformer model, we have these position encodings, even positions and odd positions, as shown here, using sines and cosines. Okay, well, how does that match up with ours? Well, in the most general sense, this is the generic form of our complex automata, complex diagonal multiset automata. So we have lambda, those initial weights. You've got some magnitude, some angle on each one of them. In the transition matrices, you've got magnitudes, complex weights, and in particular, because these are this diagonalization process, it actually depends on the eigenvalues. These come complex pairs, complex conjugate pairs. So if we're starting with real weights, which in our case we are, then when you diagonalize, you're going to get any complex number is going to come up in a complex conjugate pair. So in the general form, we have, as shown here, lambda having just magnitudes and angles, mu having magnitudes and angles coming complex conjugate pairs, which are going to then cancel off those imaginary parts when you compute the weights of any sort of string. So if we set all the magnitudes to 1, set the angles of the initial states to pi/2, set the angles on the transitions according to what's shown here, and make a change of basis to make sure that we're working with real numbers in these forward weights, then we exactly get out the transformer position encodings. So in this viewpoint, transformer position is just a unary run on this automaton where you're looking at the forward weights. So in this interpretation, transformer position coding already uses a multiset automaton run on the positions. It doesn't run directly on the words, it runs on the positions. So every time you move to a new position, you're reading mu. We don't need to have mu A, mu B, and so on, because we're just, positions is just a unary input. We just have one input being how many of these mu's are you multiplying together. Okay, so this is great. It already exists out there, and while we can match the power of the position encodings by this special setting of the parameters, if we let the parameters kind of roam free, what more can they learn? So we set this up, we tried this on a few different situations. If we're going to allow our position encodings to learn, it seemed only fair to allow the transformer position encodings to learn. So in these experiments, we show the baseline, which is fix the position encodings to match the sinusoidal ones. allow it to learn per position encodings. So that would be not using our work, just allow it to learn what these parameters are for each one. Constrain the magnitudes to 1, allow it to learn just the angles, and then finally allow it to learn the entirety of the initial weights, the entirety of the transition weights, and see what comes out of that. I'll note here that this is on a language translation task. We're using low resource language pairs. Blue is a measure of translation quality, where higher is better. So the baseline, again, is just sinusoidal encodings using our representation. We get 23.9. Per position, this is not using our representation. This is allowing it to learn what it wants to for each position. These are absolute positions that it's learning. This is a low resource setting, doesn't really have enough data to learn this reliably, so it sees a drop in its blue score. If you allow our representation to learn just the angles and you fix the magnitudes, you get a slight increase in blue score, not significant, but shows that it does at least as well, sometimes a little bit better. If you allow it to learn the full matrices, it's doing better than the per position encoding. It does suffer a little bit from the lack of data here. So low resource per position, there's just a lot of ability to learn. So you saw a drop there. We see a slight drop here, but notably it's learning a similar amount of parameters to the per position encodings, but is able to achieve higher blue score than the per position encodings. So per position hurts a lot in this low resource setting. When we ran this, learning the angles helps a little bit. And this is the average over 7 different language pairs. So in the paper, you can see which languages actually benefited and which ones got a little bit worse. And learning the full transition matrix, there's more to learn, more parameters there. And with this amount of data, it doesn't necessarily improve the system, but it is definitely better than per position encodings on this data size. Okay, so it exists in the transformer. That's great. We can actually implement it, run it, and see what happens. That works out. But we really want to explore, we were motivated by this deep sets work where we have a representation, a commutative function. Let's see when we modify deep sets to use our representation, what happens? Are there particular instances where we can show that there actually is a computational benefit to using our representation? So as a refresher, broadly speaking, deep sets compute a representation in parallel, and sum them all up, whatever commutative function, but for their experiments, they use sum, and then use that in some way downstream. In their paper, so I took their code exactly as posted. They had an input layer, size n, an embedding lookup, so 100-dimensional embedding for each of these inputs. They then ran that through a dense layer, ran the outputs of that through a summation to discard ordering information, and then finally a dense layer at the end to then output whatever they were trying to output. For our setting, we have a similar approach, complex embedding, then skip over the dense layer because we found that wasn't needed, and that seemed to just add something that seemed unnecessary to the network for these tasks. So complex embedding straight to the complex product, throw away that ordering information, and then apply the dense layer from there. So one of the tasks that they used in their paper, they showed LSTM and GRUs struggled with this digit summation task. So at the bottom left, we can see if you have, say, 1, 7, 3, 8, 5, 1, 3 as your inputs, and the input order doesn't matter for deep sets, doesn't matter for our model, but we did follow the convention of the deep sets paper where we did not artificially order these, say, lowest to highest or anything like that. We just, as they were generated in this data, that's how we fed them to LSTM and GRU. Order matters to the LSTM, so that is something that they did, and we replicated that as well. What they're supposed to put out is then the sum. So if you add up all those digits, it should sum to 28. And so in this graph on the left, that's what we're trying to output, is that 28. At training time, you see the number of digits up to 50. And then at test time, we randomly generate sequences in increments of lengths of 5, so 5, 10, 15, and so on, all the way up to 100. And we can see LSTM, if it has seen the length before, it does well at achieving this summation. as soon as it's to a length it has not seen, performance degrades rapidly until it has approximately 0 accuracy from, I think that's around 70 digits and onwards. GRU, it's not included in this graph, but it's nearly identical performance to the LSTM. Okay, deep sets does very well at this task. Doesn't matter how many digits it sees. It has a summation built into its network. It's able to produce this sum. So 100% accuracy all the way through. In our method, which is taking deep sets and modifying it to use complex numbers, a complex product as its commutative function also achieves 100% accuracy, even on unseen lengths. So that's great. It matches their performance. It's something that we're hoping would be true, given that we're adding power to their network. But it's nice to see that it does in fact do this. Where they had summation as their commutative function, we have complex multiplication. So there's no sum function actually built into our network. We're doing complex multiplication, but it's still able to achieve the same result. We then extended that task. We said, all right, same inputs. We're not modifying the inputs in any way. But now, instead of 28, I'm just going to take it mod 10, only return the units digit, so just return the 8. We're going to have this cyclic nature to it where the network needs to add up, and then at some point cycle back around, add up, and so on. It's only producing numbers from 0 to 9, and it needs to somehow learn that cyclic behavior. In the LSTM, as well as the deep sets model, at test time, did no better than random chance. We have 10 different options for the digits. And when it was given an unseen input, it just picked one. It wasn't consistent with which one it picked. So it's not that it was always picking the majority class or anything like that, because these were relatively balanced at training time, but it did no better than random chance. Our method, by contrast, was able to learn this task perfectly. It's able to produce not only the right answer for lengths it's seen, but able to generalize for unseen lengths as well. So this is a nice result, being able to show that not only does it match the performance of deep sets, which is outperforming LSTM and GRU, but on this new task where you've got this kind of cyclic design within there, the complex numbers, their angles circling around, it's got the cyclic nature built into it. It's able to do well at these tasks as well. So overall, what we've shown is we have this efficient method for training multiset automata. We move from real weights to complex weights. By doing so, we diagonalize, have less storage, no regularizer, no other artificial constraints there. Just learn the diagonal. So less to learn, easier computation, less to store, at the trade-off of moving from real to complex weights. At the time when this was published in 2020, complex weights had limited support in TensorFlow and PyTorch. I believe they have more support now. So if any of this were to be re-implemented or rerun now, there's additional complex number support there that would help it make the implementation even easier. We also show that transformer position encodings already effectively were using multiset automata with certain parameter settings. So not only does this make sense to use, but it's something that already effectively was used, just not motivated in that way originally. And then we extended that deep sets network, showed that moving from real to complex numbers, moving from these real to complex weights, using the forward weights within the network, enables it to solve a new, albeit simple task, but shows that it has this additional power, that there are new tasks that it is able to learn. The original deep sets, as well as LSTM and GRU, were not able to learn. Thank you for attending. Hopefully you got something out of this, and I welcome any